So our next speaker is a distinguished colleague, Professor Igor Mezic. Igor is a renowned expert in dynamical systems theory with applications in microfluids. And besides his theoretical achievement over the years, he has actively applied his expertise to essentially improving energy efficiency in building systems. He has founded the company EcoRhythm in the area of smart buildings and data analytics, and he's a director of UCSB's Center for Energy Efficient Design. He's going to tell us more about his work in this talk. Thank you so much, Igor, and take it away.
Sounds good. Thank you, Manoush. Can you see my screen well and hear me okay?
Yes.
Okay, perfect. So the title of my talk is a little haughty. Energy efficiency and artificial intelligence, a self-managing buildings grid complex. I should manage expectations by saying that we're kind of on the ground floor of this. I believe that in the next 5 years, we are going to see a lot of applications of artificial intelligence within the context of smart buildings and a lot more than what we're seeing right now. There are some issues. I'm going to describe them as I go, but they're getting results certainly on the research side, and I'll discuss the aspects of the implementation that are necessary to get these types of technologies to the market and improve the energy use aspect of this. So the energy use. Lawrence Livermore every year produces a graph like this that on the left has all the different types of energy production, so all the different types of fuels, and then on the outlet here has the amount of energy that actually went into services, useful stuff, and then rejected energy. And you're seeing that the rejected energy is 67.5 out of 100 quads. This is quadrillion British thermal units. That's a very, very large number. So we have ways to go in order to improve on this side. I'm going to concentrate mostly on this domain, residential commercial buildings and some aspects of industrial that contribute about 20 out of those 67.5. Then you have the electricity generation where the rejected energy is about 24.2, and transportation where rejected energy is about 22.3. As a point of curiosity, I actually went back through all the slides as I was preparing for this, all the Lawrence Livermore charts, and in 2013, for example, the rejected energy was 59. The total amount of energy that we spent went up by 4 quads, and the rejected energy went up by 8. So that's not great news. I know in 2020 things have lightened up a bit, but that's due to a catastrophe that we're living through right now. Commercial energy end usage is split between buildings, industry, and transportation. And one point on this chart that I'd like to emphasize is that between lighting, space heating, and space cooling, both in the commercial and the residential, there is the biggest kind of impact if we want to reduce the amount of energy that is being used. And of course, today a lot of commercial buildings are empty, and yet the systems in them still operate at a certain level, and so they are using energy. The problem is not easy. The complication in a modern building, it was kind of mock drawing is shown over here, is that there are many different types of systems with different physics that all combine for a pretty singular purpose, and that's to keep the occupants comfortable. So energy, to a certain extent, is a secondary thought. If you look at a large commercial building, if a yearly spend on salaries and work in general, production in general, is about 100 million, you're going to get about 2 million spent or 3 million spent on energy. So it's only 2 or 3% of the overall spend in the building, And yet there are all these systems, interconnected systems, that are allowing for that comfort to happen. And so very often the energy issues are not, top shelf, if you wish, in this context. And the technical problem is not very easy either. Here is a little movie that shows you the air conditioning in a residential context coming in, and then here is this air conditioning right next to an open window. The smart system should understand that the window is open and the air conditioning is cooling the room, and just close the window so as to optimize. The algorithms for this are starting, to be deployed on a wider scale, and they need to take into account a lot of different elements. Not to speak about the fact that if you actually take into account the whole building, the whole residential context, and you have an electric car, and you have microgeneration that I think we are going to hear about next. And there is this utility aspect over here. I picked this up from thesis, perfect thesis at Berkeley. Then you get something that is a dream: demand response electrical appliance manager that connects the residential building to all the peripheral stuff, the production, the vehicle, the transportation, and so on and so forth. And all of this has to work in unison in order to provide value. What is possible if you deploy smart technologies? Well, there is a universal agreement that 20 to 30% reduction in HVAC energy, for example, is possible. And what would it translate to in savings? About $15 per month for the average household in the US. I think we're collectively going to agree that that's not much on the residential side. At a national scale, however, it translates to $15 billion annually, and would prevent approximately 1 billion tons of pollutants from being released into the air each year. So the issue is that this needs to be done without an additional burden to the occupants. So it needs to be seamlessly and securely, and certainly provides the background for developing automation in order to provide both comfort and energy. The question that is asked very often in this context is, if you really develop an automated procedure, how well can you do? So this is a part of our own work. We have simulated this building in Las Vegas, Nevada, to see what a nominal performance building with a certain variation in parameters that is described by this black distribution here does on the energy scale for facility gas, electricity, both for the peak demand and the annual consumption. And what you're seeing here, the take-home story, is kind of the savings seem to be vast, right? So you can do really, really well in this green zone if you deploy high-performance systems inside the building. Everything shifts to the left. That is really nice. This scale is in gigajoules. Everything shifts to the left, and you can achieve tremendous saving. On average, you can achieve tremendous savings in energy. But I did mention that the top shelf item for occupants in buildings is comfort. And the essential question then is, can we achieve both comfort and energy savings at the same time? So we studied that as well. And on the left here, you're seeing something that's called the predicted mean value. There's a long formula associated with it that takes an average human metabolic rate, environmental conditions, and so on and so forth. Essentially, how do humans react to environmental conditions? If you're seeing numbers around 0, we are neither too hot nor too cold. And that's this blue area that we selected here. And we asked the question, if we take buildings within which, that provide the occupants with this level of comfort, so it's really, really good. 0 is really good. It's neither hot nor cold. what is the energy spend? And the black here gives us the full distribution of what we've analyzed, and the black here over is the full distribution, and that's on energy scale. So if you take a look at these blue buildings here, they had energy described in the blue distribution over here. So yes, some of them perform terribly on the tail, but some of them are almost, the best in the context of what comfort is. So this conundrum between energy and comfort doesn't necessarily need to exist. The point that I'm trying to make here is that they can coexist. So you can design buildings that are extremely comfortable, that at the same time spend low energy, and that does away with that old joke that the best way to save energy in buildings, of course, is to turn all the systems off. We have done also the same thing on the energy side. So we selected buildings that have very, very low energy expenditure in total. And then here is the green distribution here, showing you that there are many buildings that are at the same time around 0 in PMV, which means that the occupants would be very comfortable. So one can achieve comfort and energy, but what I've just shown you is kind of a fundamental knowledge base, right? Right down here on this huge diagram that says, oh, we need to understand the energy and comfort in buildings. Let's develop model predictive control, optimal algorithms for building grid awareness, and so on and so forth. All of this is happening in academia. There are barriers to understanding, and that's the ground floor. The first floor is really implementing this in various different domains and systems: optimal demand response, integrated building system, energy storage, distributed building grid dynamics, and so on and so forth. And you have a large number of barriers there. I would select this one to be quite important: building system non-uniformity. If you go to the top floor, you have an integration across the board. Secure distributed building grid control, so security comes into the question. Building grid energy optimization, and so on and so forth. And then finally, products and outcomes go to utilities and building owners, operators, and the requirements are fed back in there. And in the panel, hopefully we're actually going to talk a little bit about how these requirements are propagated all the way down to fundamental knowledge base, some of which we still have to develop. Don't worry, everything's fine. We have the solution, and here it is. Some equations. External drivers are complex. We need energy forecasts. We need weather forecasts, thermal comfort constraints that I just spoke about. We certainly need either a model or the data from electric grid. Data on electric grid is hard to come by. Multi-zone energy system models, or we could replace these bottom two by data-driven models. I think Sila was talking about data-driven models. That's something that in my research group is being developed as one of the main topics. So instead of physical models, just let's go from the data. But then we need to build algorithms that optimize. So this meta system optimization that integrates commercial building portfolios with electric grid systems. First on the side of zones, building. Then we go to portfolios that might be somewhat homogeneous, and then heterogeneous portfolios, and we finally get to sustainability that is similar to the background that I have in the Zoom right now. What is our approach to those points? Well, we start from sensor inputs. Everything that we do is actually data-driven, and we pursue whole building analysis methods. So what you're seeing on the left here is a description of a physical field in a building. What you're seeing down here is red. It doesn't necessarily mean the temperature. It actually means that that particular zone is suspect as far as the comfort of the occupants and or energy usage in there. And this is a building in New York that we've tested this on. So then you can ask the question, well, if there is an energy use or comfort problem over here, what caused it? So this diagram here shows you at least the output of the method that says what caused it. If you're seeing, so on the horizontal, we usually plot the parameters that impact the energy and comfort. On the vertical, the energy and comfort themselves. If you're seeing red, that means that that particular parameter, I'll speak which ones influence things the most in a second, but that this particular parameter influences, for example, comfort and energy somewhat. Light blue is not bad, but it's not very good either. Dark blue is good. This is based on a analysis both from models and from data that involve a lot of steps in model reduction and validation and so on and so forth, because even the models that we get are actually huge on the computational side. So once all this information is available, there are actionable recommendations for the buildings that can be done either through the actuators or through the action. Sometimes you do need people to go and unstuck a valve. So that is a common recommendation, in fact. So there is still something to be done on the physical side there, but some of the common items that need to be corrected are actually software based, and they can be corrected in an automated way. The promise is then that we have lower energy cost, improved comfort, and an integrated smart home on the residential side. What do the sensors look like? There is an Omron sensor that we actually deployed in our own lab: temperature, humidity, light, sound, noise, UV index, and so on and so forth. And then you can plot the temperature, let's say the indoor and the outdoor contrast using algorithms between these two and other aspects. So when you have these sensors positioned, this is actually the Stanford Precourt Institute building, I guess a competitor, right, John? Precourt Institute building that sent us some data, and you see black dots, you see the sensors. And one thing that I want to emphasize here is how dynamic buildings can be. So hopefully you're seeing the building breathing over a variety of days. When you're seeing this blue coming in, that's the nighttime cold up in the Bay Area. The key point, and so you saw a little bit hotter day. The key point here is you're looking at the temperature field and you're seeing that it's very dynamic. And there are areas in the building that from time to time get really cold. There are areas where there are data systems and so on. So this kind of information provides us with the ability to analyze what affects the energy and the comfort in a dynamical environment like this. And so this graph here is showing you the variety of parameters: heating source, cooling source. Let me go down here. External zone, this is the building envelope. Internal zone, this is the schedules. And then you have zone set points. And the thickness of the lines indicates how much that parameter has an effect on, say, facility gas, electricity, heating, cooling, pumps, fans, interior lighting, and so on. And here is a really remarkable thing. The schedules, zone internal, and the set points, right? So temperature set points have the thickest lines when you go to facility electricity and facility gas. So interestingly, the biggest impact in energy savings is in fact within kind of software controllable pieces. So schedules and set points. And those, to a certain extent, are the hardest to optimize because they, of course, depend on many different factors. Like I pointed out, the external factors like weather, but also internal, like occupancy. And we don't have a massive base of buildings that have occupancy sensors. Combinations of those factors can be important as well. Here are all kinds of failures that you can identify with this kind of analysis, but I'd like to point you to this table that says, okay, night set point temperature set incorrectly, and night set point temperature set, and then various other examples of lighting not turned off at light, improper. All of these things you see in buildings that you can calculate their influence. Calculate their influence on the outcome and the energy spending. And it's very often that combinatorial effect failures are more critical than the sum of parts, and this is where the whole concept of artificial intelligence goes in. So we do a lot. We eat a lot of our own food, prepared food. So we implemented some sensors in the old lab. This is what the old lab looked like. The new lab is much nicer. So the Omron sensors are developed over here, and you can do a lot of fun stuff on these. So for example, you can take a look at what your overall comfort and energy use look like. This is one of the modes, and if you're seeing dark blue, seeing it's a relatively good situation. If you look at the 15-hour mode, that's really repeating between 12 and 15 times a day. That's actually the operation of the control system, and you see that it's non-uniform. You certainly don't want to see that in an intelligent system operation. So you can sort of automatically, the differences here are not huge, but you can sort of automatically calibrate for that. And you can do some fun stuff and ask what is the phase of the different modes. And if you're seeing blue here, that's one phase, and that's the phase that starts at about 9 o'clock in the morning and finishes in the afternoon. And then there is the yellow phase. Now, the reason why I'm smiling or laughing is that this doesn't necessarily have to do much to start with energy, but it turns out that my students that are sitting here are in an entirely different phase than the postdoc that was sitting here. That was kind of an interesting thing to observe in the lab as a consequence of trying to do energy monitoring.
Hey, Igor.
Yes.
Oh, there you go. Okay, I was going to ask you. Okay, sorry.
Right there. So in conclusion, we focus on integration of software tools, development of artificial intelligence and energy space. We have some good underlying algorithms. I hope you saw from this perspective that commercial buildings do offer massive opportunity for energy efficiency, reduction of energy costs. The problem with the residential buildings is the savings are relatively small on individual residential building, but they're actually large overall. Extracting efficiencies from buildings and grid operation together can yield large energy savings, and I'd like to thank Zaleski Foundation on funding part of this work. That's it.
Great, thank you so much, Igor. That was a very insightful talk. I guess we have one question from Jordan Pinzel. Are there issues associated with the computational expense of solving these complex models in real time? Are the timescales of solving the models and driving actuators the same?
That is an excellent question that I didn't get into, but one of our latest research work pieces is exactly producing the models that can run those kinds of computations on the edge, meaning on the chips that could be embedded within the building system. Referencing things like Energy Plus models that can be done offline give a certain level of prediction for building energy use, but you really cannot run them online in the control setting. So when I said model reduction, that's precisely what I meant. So one of the issues is to develop the models that in fact are capable of running in real time and changing the comfort and energy parameters in order to achieve it. And that's something that a number of groups around the country and the world are working on. We have specifically also done some work on this in the last 2 years. If you have an interest, I can send you some papers.
Great, thank you so much, Igor. There's one more question. Anonymous attendee asks, you talked a lot about human comfort in design for building energy efficiency, and I was wondering what kind of metrics you're using for this. I've recently come across a study that shows that building thermal standards are generally outdated and don't accurately account for women's lower metabolic rate contributing to their freezing at work.
What we used in this contrast here is, let me see, in this one is the predicted mean vote. That actually does take into account the metabolic rate.
Excellent. Thank you so much. Are there any other questions? I mean, John has a question. Go ahead, John.
A couple. So in Henley Hall, the lighting and heating should automatically reset independent of what people have manually set. So in terms of, you pointed out that was a big problem in, I guess, the pre-court study. So hopefully this Henley Hall will look much better, you think, or perform much better?
We definitely hope so. We're certainly going to be doing the measurements within the, within the lab to try to understand that. But the way it's been designed to perform at the peak of what the load in that building can allow, right?
So in terms of measuring comfort and people's satisfaction, that'll be interesting. For things like the auditorium, that's not going to be cooled unless there's people there, right? That automatically, at least the default is that we may want to adjust it so if there's something scheduled, it starts cooling ahead of time, right? But
yeah.
So you'll have to work out more sophisticated control, I think, than what's set up now. When will your model for the building, like you showed here, be up and running?
Well, so we're working on it. The best way to design a model for the building is to actually validate it as we go, right? So we all know that if you do offline design, that the predictions for real building in operation can go, 30, 40% off, even more. That was actually the case with the building that I've shown. That is not ours. The best way to do this is to calibrate the model as you go. That's one aspect of the story. Of course, this building has, the atrium has a lot of non-conditioned spaces, and whenever you have that, interesting physics shows up. So I predict it's going to be interesting to watch as to how the kind of standard models are going to perform versus the new models that we have designed just recently that take into account kind of the whole dynamics of the building in a data-driven way instead of modeling individual spaces from kind of first principles. And there is certainly a huge debate out there in the research world as to, what is a better approach. I trust that with a lot of unknowns and uncertainties like you have in buildings that have non-air conditioned spaces, it is a better approach to go data-driven and produce models of that kind.
Okay. Thank you so much.